Greetings everyone. This particular video is going to focus on talking about the force of friction in a bit more detail. Right? We've talked about friction in a very general way, and basically the main thing we've talked about so far is that friction is something that seems to resist motion. Right? Now, the force of friction will always go opposite either the way that I am moving or I am attempting to move if there is friction involved. All right. Now, what we're going to do today is we're going to talk about in a bit more detail what exactly friction is and how we can actually calculate how much friction something might exert on something else. Because we're going to find out that that's going to be exceedingly important for a lot of different things you run into in physics. Because unfortunately, no matter how much we try to get rid of it, ignore it, or reduce it, friction is always going to be a part of kind of what happens in the physical world. And it has some very important properties that we want to address. All right. Now, what we're going to talk about first is how friction actually works. All right. Now, friction at a basic level, a microscopic level, if I was looking at it with a microscope, looking at surfaces, what you would see is that every surface you look at is not smooth. Even things you think are smooth are actually deep down at a microscopic level rather rough. You're going to see a lot of little hills, a lot of little ridges, a lot of little things that suggest that, stuff could get caught in. Now, what happens is that when you take two surfaces and you put them on top of each other and you try to rub them together, all of these little hills and little holes and little valleys and little peaks basically get stuck between each other. And as you try and move them, so as you basically try and take one surface and try and pull it across the other, all of the little ridges and stuff get stuck together. And they basically hold both surfaces in place at a microscopic level. All right. Now, when this happens and the two objects don't move, so if I'm trying to pull something and it is stuck, we call that static friction. All right. And that's a very specific type of friction that basically happens when two surfaces are basically stuck together, and no matter how we try to pull one across the other, it will not let them go because all the little ridges and valleys are kind of caught between each other. All right. Unfortunately, there's a limit to how much these ridges and valleys can kind of exert forces on the other ones before some of them start to break off. All right. And what that happens is that imagine if we, let's say in this case, you'll notice I have two little diagrams. One of them represents the bottom of a cinder block. One represents a concrete floor. Well, let's say I eventually basically start pulling on the cinder block so hard to the right that I actually start to shear off and break pieces of these little ridges and little valleys and whatnot, and basically make it appear smoother. Well, what happens then is that now I have basically made it so that the force of friction goes down a little bit. And what will start to happen is that the cinder block is now going to start to slide across the concrete floor. It'll still experience some friction because it's still going to experience kind of that interaction between its ridges and valleys and the ridges and valleys of the concrete floor. But because the cinder block is now smoother, that force of friction is not as great. All right? And what we refer to that now is that when you have friction between two objects where one is sliding across the other one, we refer to that as kinetic friction. All right? And that actually acts a little bit differently than static friction. Now, that's how friction works at a microscopic level. It's just basically a bunch of little peaks, valleys, ridges, whatever you want to call it, getting stuck between each other and eventually keeping two things from moving. All right? To actually see it in action, we're going to open up this little friction lab simulator. So if you could, you're going to open up this link. It'll take you to something called a friction lab. Now you notice there's a big blank space here that says notes on friction. I am not going to tell you what notes to write down here. I'm going to give you a little leeway of your own. You write as much or as little notes on friction as you want. All right, but use this space accordingly to kind of discuss. I'm just going to narrate a little bit about what's going on. Be aware that there are two big questions I want you to think about. And the first one is, how does the surface force on an object affect the friction on it? And how does the surface itself affect the friction on it? So think about those two questions, please, while I'm kind of talking about this. So if you open up the friction lab, you'll notice it looks something like this. All right, and it's got a big object with a rope attached to it, and someone's pulling on it with a force probe. So what that means is this is recording how much force it's pulling on the box with. All right. Now there's two things you can change in this scenario. You can, one, change the surface that these two things are on. So in this case right now, this is an aluminum box on a steel surface. I could change it to say this is a glass box on a glass surface, graphite on graphite, rubber on concrete, wood on lab table, and rubber on ice. All right. Now remember, in all these cases, I'm changing the surface itself. Now, the other thing I can do is I can actually affect the mass that I'm putting in here as well. All right. And in fact, what I'm doing right now, it's going to go about right around 1,000. That's about half, looks like half you can do. Now, what I'm going to do is I am going to pick, I'll do rubber on concrete. All right. And what I'm going to do is I'm going to hit start, and I'm going to start pulling this to the right. And what we're going to do is, you'll notice once I hit start that there is a force graph that's going to start to be generated down here. All right, so I'm going to hit start, and first we're just going to watch what happens. So I hit start, and you can notice right away that this person is applying a force, and it seems like nothing's happening at first, and then eventually all of a sudden something starts to occur. Now I'm going to reset it, and this time we're going to do it where we're actually going to watch. It's going to graph the force being applied by the person and the time going by. So this time, all right, I'm going to hit start, and something interesting starts happening. So the force is going up, it's going up, it's going up, and all of a sudden, boom, it goes down, and it looks like this. All right, now together, if we zoom out, let's watch them both together. So I'm going to reset this, and we're going to watch. So now I'm pulling, pulling, pulling. This thing is not moving. The amount of force I'm applying is going up. And then eventually I start to get it to move, and all of a sudden this force I'm applying with drops down. All right, now I'll tell you a couple things about what's happening here. First off, I'm trying to pull this at such a way that it moves at a constant velocity to the right. Okay, that's what I'm doing right now. You'll notice that there are two things going on here. In the first section, this weird line that kind of goes up and up and up and up and up, this is actually representing what we refer to as static friction, all right? Because what is happening is I'm pulling on this box, but as we kind of talked about in our notes, all the little ridges of the rubber box and all the little ridges of the concrete floor are currently stuck together. And I'm not exerting enough force yet to kind of overcome all those little ridges. So, because of that, I'm pulling with more and more force, trying to overcome those ridges. Static friction works just like that. Static friction in a way is almost like it's a limit, all right? And what that means is that static friction basically can be any value that is less than or equal to the maximum friction value a surface can exert before basically you break all the little ridges, all right? So what that basically means is that there's a certain point, there's a maximum amount of static friction force something can exert. And if you go past that, all the little ridges start to break off, and all of a sudden it's not resisting as much anymore, all right? So right in there you see the first thing, static friction works just like that. The second piece is kinetic friction. Now, once you get something moving, what's rather interesting is that kinetic friction actually, is a very consistent quantity. Kinetic friction does not change because basically you can kind of assume, the way we're going to think about it, that once you've kind of worn away the little ridges and whatnot on one of the surfaces, it's going to stay like that for the rest of the time. So kinetic friction acts as a very consistent value, all right? Now, this is going to be important because we're going to talk in a little bit about how you can map out these two things. But the key issue here is that static friction is always stronger than kinetic friction, all right? And a way you can kind of think about that is that if you've ever tried to move anything, or if you have anything heavy in your house, all right, try and push it. And you'll probably find that it is harder to get something moving, especially if it's maybe really like getting stuck on the ground, than it is to keep it moving. And the reason is because you're seeing this idea of friction. It's much more difficult to overcome static friction than it is to kind of keep things going with kinetic friction, right? And it all has to do with that idea that basically those little ridges and valleys are getting broken off because you've exceeded the force they can exert to resist motion, all right? Now, you'll see the maximum static friction force in this case is about 9 newtons. That's the most friction this thing can exert and not break. If you go any higher, all of a sudden, all the ridges start to break and it starts to move now. All right? Now, let's kind of notice there's two things we can change. All right? Well, let's change how much mass I have in the object. All right, so let's say I have 1,000 grams. Let's say I bump it up 2,000 grams. All right, so remember, it was about 9 newtons was the maximum force. And here, oh gosh, you'll notice I've doubled the mass, and it almost looks like it now takes about, it was originally 9 newtons, it's about 18 newtons now, it looks like. That's the maximum static friction force before this object can start moving again. All right? Now, what I've done is I've increased the mass of the object. And at first, it can seem like that means that the weight of the object is what matters when we talk about the force of friction. But in fact, the force of friction is not, it doesn't really depend on the rubber box here. What it does depend on, however, is the other force that the surface exerts, right? And what that means is that as this box weighs more and more, that means that the table has to push up with more and more force to balance it out. Because of that, what happens is that you can almost imagine that the two surfaces are now pushing against each other with more force. So all those little ridges and valleys are even more jammed in together, which means that it actually exerts more, it takes more friction force to break all of those little ridges and valleys this time to overcome that static friction. So what we're going to find out is that with friction, one of the ways you can increase the amount of friction something exerts on something else is to increase the normal force, increase the surface force on the thing that's trying to slow down the other thing. All right? Excellent way of thinking about it is to think about your car brakes. If you've ever seen your car brakes, and if you haven't, it's always good to kind of understand how your car works. Car brakes are very simple. When you step on the brake pedal, two brake shoes, which are just basically two pieces of ceramic or metal, whatever you have, basically start to clamp down on one of the wheels. All right? And the harder you step on the brakes, the more you clamp down on the wheel. And as you clamp down harder and harder on the wheel, you generate more friction to slow down your tires, or slow down your wheel in this case, because you are increasing the surface force. All right? Now, that's the first way you can change. You can kind of change the force of friction. The other way, so if we go back and we kind of reset, go back to 1,000 if we can, or somewhere close, all right, is we can also change the surface itself. So right now we have rubber on concrete, and concrete is pretty rough. All right, if you ever run your hand across it, if you've ever accidentally fallen on it and skinned your knee, it's pretty rough. But if I change it up and maybe I go to like rubber on ice, right? Ice is pretty slick. So let's see what happens. So if I hit start, all right, you'll notice the same thing happens at first though. I have to apply a force. Ooh, my apologies. All right. And at first, nothing happens because I have not overcome static friction. But if we look at this time, remember, for 1,000 grams, it took about 9 newtons on the concrete to get it moving. But here on the ice, you'll notice that now it only took about 1.2 newtons to get this whole thing moving. The force of friction was significantly weaker. Now the only thing I've done is I've changed the surface that I'm on. I haven't done anything else related to the mass. So what we're going to find out is that the other piece of the puzzle is the actual surface itself. All right? And we're going to figure out that there's something that we refer to as the coefficient of friction, which is basically the best way to talk about it is it's a measurement of how sticky the surface is. All right? How many of those ridges and valleys and all those things are there at a microscopic level. So, with that being said, that kind of gives us a way to answer our two big questions. So our first big question, how does the surface force on an object affect the friction on it? And what we're going to say is, the more a surface pushes on another object, the more friction it can provide. All right? And then how does the surface itself affect the friction on it? And we're going to say, the stickier a surface, more friction it provides. And you say stickier, the rougher a surface, really doesn't matter. Any way that you just give yourself an idea that that quality gets stickier. All right? Now, all these things, fantastic, all these general notes, but let's actually pull them together and let's talk about how they relate to formulas. So, on the second piece, we start with something that says the force of friction equations. All right? Now, you notice there are two different equations here, and the reason is because there are two different coefficients of friction, all right? And the reason for that is, again, kind of similar to that idea about how when things are in static friction, all those ridges and valleys are intact, but for kinetic friction, we've accidentally broken some of them, so the surface itself has changed. So, static friction is written in a very strange way, but you write it not as just an equals equation, but it's an inequality. And what it says, is that the force of static friction is always going to be less than or equal to the normal force, all right, or the surface force, acting on the object, times something that we haven't seen before. It's a special character, all right? And we call it mu. And it looks like a weird little u, mu, all right? Now this mu is just another fancy way of saying stickiness, all right? And we're going to put a mu s to represent that this is a static friction coefficient. So what this does is these two things dictate how much static friction is going to be exerted on an object. And because of the way we've written it, what it means is that this static force to static friction can equal anything between 0 up to whatever this value is, whatever the normal force times the static coefficient of friction is, all right? Everything in between that, just like we saw in the lab, just this little line right here, everything in between it is fair game depending on what force you're exerting, all right? Now for kinetic friction, again, we talked about the idea, this is consistent. This does not have this weird limit action that the other one did, so it's much simpler. Kinetic friction is, again, dependent on the surface force, because if, again, you want to think about it, if there isn't a surface pushing on another surface, then there can't be any friction. Times another one of these weird little mu's, but this time with the little k next to it to represent the coefficient of kinetic friction. All right? Now, again, this can be very strange at first to think about, oh, there's kinetic friction, there's static friction. All it comes down to is this idea that for static friction, you have all these little ridges and valleys that are interacting with each other and not allowing the other one to move. For kinetic friction, some of those ridges and valleys have broken or filled in or whatever, which means now they are allowed to start sliding because they can't resist whatever force is being applied anymore. All right? Now, first question. It says if I apply a force of 20 newtons to the box to the right, but it doesn't move, what is the force of friction on it? All right? Well, what I would suggest is you want to start by think about what's going on here. All right? It says I'm applying a force of 20 newtons to the box to the right. All right, so if I was drawing an FBD, I would have applied force going to the right, and it would be 20 newtons. But it says it's not moving, which tells me that something is probably holding it in place. All right? Now, what that means is that more than likely there's probably friction resisting my motion. And because it says it does not move, that means it has a constant velocity of 0. All right? Now, if it's got a constant velocity, what that means is that the forces are balanced on this object. And if the forces are balanced, if we said there's an applied force going to the right with 20 newtons of force, that means that the force of static friction is also going to equal that same thing. So we're going to say static friction is also equal to 20 newtons. All right? So, what we're seeing here, I apologize, my spelling is not great today, is just this idea that friction you always need to follow the rules, all right? It's not suddenly coming up with new rules we haven't seen before. We're still following the same rules we talked about. If it's going at constant velocity or not moving, then the forces are balanced, all right? And again, we talked about it. This type of not moving friction is referred to as, and we already said this, static friction. Now, I keep pulling because I really want to get this box to start moving, and eventually I pull with 50 newtons of force, all right? Once I get to that, and I pull just a little past 50 newtons, the box begins to move. What that means is you'll notice I say, what's the maximum value of static friction force? Is that basically up into 50 newtons, the friction is strong enough to not allow anything to move. But if I go past that, even the tiniest bit, above 50 newtons, it's now going to allow it to start moving because I've overcome static friction. So that means the max static friction value, the most it can exert, is equal to 50 newtons. All right? Now, one of the reasons this matters is because a lot of times I'm going to ask you to use values like that to figure out how sticky a surface is, because we're going to find out it is very important to know this, especially for a lot of things that involve things on hills or things that involve things at angles. And we're going to start talking about that the next couple of weeks, the idea of what happens when forces aren't just going up, down, left, and right. Okay? So, what's nice is that I want to find the stickiness. All right? Well, if you know the max static friction force, you don't have to use that weird inequality anymore. You can say this is now equal because that is the highest value it's going to be. all right? And using our lovely little formula, all right, we see that the force of friction for static friction is equal to two things multiplied together. Now, remember, we're actually looking for the stickiness, so we're looking for this weird little mu thing, all right? So, move some stuff around. In this case, you can kind of see, just kind of looking at what we got, mu is going to be equal to what looks like FF divided by Fn. So we're going to divide the force of friction by the normal force of the box. All right. Now, you notice I'm not, there's some things I'm not really super explaining. I'm not really touching base on everything. We've missed a couple things. We haven't drawn our FBD. All right. We could if we wanted to. And I know I've said that's part of our problem solving process. Right now, we're just kind of going through and taking what it tells us in the question. All right. So in this case, it's equal to the force of friction divided by Fn. Well, I know the force of friction, or the max force of friction, which is going to be 50 newtons. However, I'm at a bit of an impasse because I don't know the normal force yet. All right. But I do know if I look at what the diagram is, which is the little picture up here with the box, all right, you'll see that it has a mass of 10 kilograms, which means to find the weight, if we think about it, the normal force is going to be opposite the weight here because it's not falling through the floor at all. So the normal force is just going to be equal to the weight of the box. And since the weight of a box is just its mass times the gravity field, which is 9.8, 10 times 9.8 is going to be 98 newtons. So in fact, the coefficient of static friction is going to be 50 divided by 98, which is going to be slightly greater than 0.5. And give me 1 second, I'll tell you exactly what it is right now. Okay, so we went 0.51. All right, now that is a measurement of the stickiness. And right there, that tells you that number gives you an idea of how sticky the floor is. Now, that would be very useful because imagine if I wanted to now figure out how much force it would take to move something much larger. Now that we know the stickiness, I can figure out what the maximum static friction force is for a new object, and I can predict how much force it'll take for me to apply to get it moving. All right? Now the final piece here. It says, now I begin pulling the box at a constant speed. So now it's moving. 30 newtons of force. What is the force of kinetic friction now? Again, it says I'm pulling the box at a constant speed, which means I have balanced forces. All right? And because I have an applied force of 30 newtons, that means the kinetic friction force now is going to equal 30 newtons. All right? And again, I am not doing the things I'm supposed to be doing, which is I'm not drawing FBDs at the moment. I'm not really pointing out. I'm using what I know in the question, but we want to start getting comfortable with this idea we can take these context clues in the question and know what force is equal to what force. But I highly recommend in your notes, draw an FBD somewhere. All right? Make sure that you have an idea. If you're not quite sure what I'm talking about, put the FBD in there. All right? So if the kinetic friction force is now 30 newtons, again, we're going to go through and use our new formula. It says find the kinetic coefficient of friction. All right? We use the same formula as before. FF equals Fn times a little weird mu, and this time it's mu k. All right? Now, again, you're going to solve for it just like we did before. So you're going to do the lovely little stuff where you have mu k. It's going to be equal, not mk, undo. Mu k is going to be equal to ff divided by fn. My apologies, it's definitely going a little nuts today. That's all right. So, it's going to be mu k is going to equal ff divided by fn. We know all these values. All right, F of F in this case, the new friction force, because it's kinetic friction, is 30 newtons. And again, it is 30 newtons because it says the box is being pulled at a constant speed, which means it's experiencing balanced forces, which means that it has to be the same as the pulling force. And since the pulling force is 30 newtons, the kinetic friction force is also 30 newtons. All right, and again, we're going to divide it by the same normal force. And because we haven't changed anything about the box, the normal force is the same as it was before, which is just the weight of the box, which is 98 newtons. So, with all that being said, you get that it's going to be 30 divided by 98, which is going to be roughly a little bit greater than 0.3, which specifically is going to be 0.306. All right, and again, you can see just by looking at it, this coefficient of friction, the stickiness, is less than the static coefficient of friction. All right, so I'm well aware this is a strange topic, and I know this is only just kind of starting talking about how friction works in a bit more detail. If you are confused or you have questions, please come to office hours because I'm happy to explain, and this is definitely something that can be very strange at first. All right, so with that being said, y'all, excellent work. Feel free to shoot me an email if you have any questions. Otherwise, have a great rest of the day.